Hello, everyone. Welcome in. We're going to just hold on, sit tight. We're going to get started here around 2:05 for you. Alrighty, everyone. We'll be beginning here in just about a minute or so. Just go ahead and hang in tight for us for you. Alrighty, hello everyone. Welcome to Rolled Alloy's second webinar for this series. Today's webinar is going to be on the introduction to heat-resistant alloys. First off, I'll get off showing you what we're going to be doing today. Today we're going to be going over a rolled alloys overview, a heat-resistant alloy overview, and what it is, how they're used, and what to consider when you're looking into heat-resistant alloys. We're also going to be looking at specific applications, and then we'll save a Q&A section for the end. So we'll keep all questions to the end for us if that's okay. Rolled alloys overview. We are a global supplier on the specialty alloy side of things. We offer state-of-the-art material processing, best-in-class e-commerce site, and a metallurgical expertise who is speaking with you today. We offer alloys that grades of alloys as nickel alloys, stainless steels, duplex, titanium, and cobalt, and a various range of forms, plate, sheet, and bar, and others. Further on the rolled alloys overview, we offer a different array of state-of-the-art processing for you. We offer laser cut, plasma, water jet, an abrasive saw, and a couple other different processing capabilities for you. We allow customers to send in drawings for custom cut parts and other things like that. Today's speaker is Hugh. Hugh is an application engineer with the Metallurgical Services group here at Wrought Alloys. He has a Bachelor of Science in Mechanical Engineering from the University of Toledo School of Engineering. He's been with Wrought Alloys since 2019. His duties include performing an analysis on failed components, answering technical inquiries, supporting customers with material selection for specific applications and processes. Hugh currently serves as a member of the ASME, or the American Society of Mechanical Engineers, MTI, or Material Treating Institute, is also a voting member for committees E and F for the AMS specs on the SAE AMS spec standards, and also a part of the Association for Materials Protection and Performance, or AMP. All right, I will be now passing you guys along to Hugh, and enjoy the rest of the presentation.
Thank you, Garrett, for that rousing introduction. Before we begin, I'd like to mention that this webinar is now the second in a series of webinars that we will be conducting in the future. If you'd like to view the first webinar, you can navigate over to the Wrought Alloys webpage. And the first one is called Specialty Alloys for Space Exploration. So before we begin today, I'd just like to discuss some of our metallurgical services. Wrought Alloys has a metallurgical services team dedicated to serving our customers. We have a full service laboratory where we're able to conduct failure analyses, oxidation and corrosion testing. We also offer positive material identification. And we also have a sample coupon program where we're able to supply you with samples to test within your process to get real world analytical data. So without further ado, we'll begin the presentation. So what is a heat-resistant alloy? A heat-resistant alloy is any group of stainless steels or nickel alloys that are produced specifically for high-temperature surface environments. These alloys are going to require at minimum 12% chromium to form a chromium oxide layer. These materials are further enhanced by the additions of carbon, nitrogen, as well as nickel for higher strength at temperature. Silicon and aluminum is also added to the microstructure to create a suboxide layer below that of the chromium oxide layer. Rare earth metals are also added for better oxide adherence. Some common specialty alloys or specialty high heat resistant alloys are going to be Ra253Ma, 309, as well as 310. Some common nickel alloys are going to be Ra330, the 600 series alloys with their increasing levels of nickel and alloying elements, as well as 800H and HT that has additions of carbon, as well as Alloy X that was designed for marine applications as well as aerospace applications. So some factors to consider when selecting heat-resistant alloys. I know many of you are familiar with this one, and this is a subject that's been covered quite often, but oxidation. Oxidation is the high-temperature chemical reaction of a metal with the oxygen in the atmosphere. Heat-resistant alloys with at least that minimum of 12% chromium are able to form an adherent oxide layer to protect it from high-temperature applications. Exposure in excess of these temperatures beyond the oxidation threshold can cause these alloys to become porous and thick. As you can see in the microstructure to the right, the material at the surface has become brittle and porous. I should mention that this oxide layer is protective up until you surpass that oxidation threshold. After that point, the material will likely spall and contaminate your process. So this chart here is just showing you just different alloys from the austenitics to the nickel alloys and showing their oxidation thresholds. As you can see at the very top, we have the 18-8 stainless steels like 304 and 316. And as we go down the scale, we have the nickel alloys, and as they increase in nickel content as well as alloying elements, they're able to withstand these high temperature applications. As you can see, Ra60TCa has an oxidation threshold of 2,250 degrees, making it one of the most oxidation resistant materials out there. So this is actually a test that we performed in-house in our Wrought Alloys laboratory. As you can see, the sample on the left has maintained its shape through the duration of the testing, while the sample on the left has become porous and brittle. This is pretty much what you can expect when you design for the correct application. It's best to select material that is working within this oxidation threshold so that it can maintain its shape and integrity. The next factor to consider when designing for high temperature applications is going to be creep strength. Creep is a time-dependent deformation at elevated temperatures and constant stress. As you can see in the picture to the right, 321, 310, and 601 and Ra253 were tested at elevated temperatures for an extended amount of time. 321 and 310 have buckled under the pressure of its own weight, while 601 and Ra253MA have maintained its shape through the duration of the testing. An alloy with high creep strength will retain its shape at temperature, while a low creep strength alloy could be susceptible to buckling under its own weight. Another thing to consider is when designing for these high temperature applications, above 1,000 degrees, it's best to consider creep strength. Below 1,000 degrees, it's best to consider yield and tensile properties. So here we have a comparison between different creep strength of various alloys. Just to give an example, Ra253MA at 1800 degrees Fahrenheit requires 0.89 KSI to deform by 1% deformation in 10,000 hours of testing. Another example is Ra330 at 1800 degrees requires 0.5 KSI to deform by 1% in the same 10,000 hours. The lower stress values at a given temperature will result in less than 1% deformation in 10,000 hours of service. So the next factor to consider is if you're going to be operating in a carburizing environment. Carburizing creates a tough, wear-resistant layer through the diffusion of carbon into the surface of the microstructure. The process of carburization increases the hardness and wear resistance, but it often reduces the ductility of the material. In carburizing environments, heat-resistant nickel alloys are often better to resisting heat-resistant stainless steels. Some commonly used alloys are going to be Ra330, 600, 601, and Ra602Ca. Very similar to carburization, you also have nitridation and nitriding. Nitriding is the heat treating process that diffuses nitrogen into the surface of the metal to create a case-hardened surface. As you can see in the picture on the right, this process creates a thin, hard layer on the surface of the steel that is more wear-resistant than the steel that has not been treated. Very similar to the carburizing environments, it's best to select an alloy with high nickel content to better resist the nitriding atmosphere. And once again, these materials are going to be Ra330, 600, 601, as well as Ra602Ca. So when considering operating in vacuum, creep strength and process environments tend to be the main consideration when selecting materials for these applications. In vacuum, the process environment should be void of oxygen, therefore removing the risk of oxidation forming on the material. Some common processes performed in vacuum will be carburizing, nitriding, as well as annealing. So switching gears here, we're going to now speak about things that you can commonly run into in these high temperature applications. The first is going to be sulfidation. So nickel alloys are vulnerable to sulfidation attack, especially in reducing environments. Nickel reacts readily with the sulfur to form a low melting eutectic compound known as a eutectic. This eutectic lowers the original melting range of these alloys from between 24 and 2600 degrees all the way down to 1175 degrees. Alloys containing over 20% nickel tend to not be suitable for these sulfur-bearing environments. So if you are operating in an environment that contains sulfur, it's best to consider Ra253Ma, alloy 310 or 309, as well as 446. So the next topic we're going to cover is going to be sigma phase. Long and short, sigma phase is an intrametallic embrittling phase that is non-magnetic. As you can see in the microstructure to the right, the arrows are actually pointing to areas that are more rich in chromium and iron. Sigma phase tends to form between the temperatures of 1100 and 1600 degrees over long durations of time. During operating during operating temperatures, sigma phase is of little concern. It's once the material returns back to room temperature where it can be likely susceptible to brittle fractures. Sigma phase tends to precipitate only in alloys that contain less than 35% nickel. Some alloys that contain at least 35% nickel are going to be Ra330, Ra602Ca, the 601, as well as 600 and 625, as well as alloy X. So the last thing we're going to cover here is going to be sensitization. Sensitization is the precipitation of carbides at the grain boundaries. As you can see in the microstructures, one sample is not sensitized. The sample below being sensitized, you can see the grain boundaries have grown. These grain boundaries are now leaving adjacent regions depleted of chromium. Once this chromium has been depleted, it will make them susceptible to intergranular attack. Sensitization can occur when a material is either operating or slowly cooled through the range of 900 degrees F to 1500 degrees Fahrenheit. So before we conclude today, I'd just like to discuss some applications that really commonly use these heat-resistant alloys. The first is going to be the thermal processing industries. Oftentimes, you'll see heat-resistant alloys for bar baskets, serpentine grids, radiant tubes and retorts, as well as muffles. You'll often find in the chemical processing industries that heat-resistant alloys are often used for flare tips, as well as calciners and the flights within the calciners, the pipe and piping support systems, steam methane reformers, as well as heat exchangers. And some other applications where heat-resistant alloys are commonly used as well is going to be in the power generation industry, aerospace industry. It can be found in galvanizing lines, the oil and gas industry, as well, and the whole reason why we're here, the steel manufacturing industry. Thank you for joining us today. And if you have any questions, please leave them in the chat, or you can contact me at my email or the phone number provided. And if you have any technical questions to submit, please check us out at the helptech@rolledalloys.com. We'll also be attending the heat treat at Detroit at December 17th to 19th. Thank you for joining us today.
Thank you all for joining us here today. Thank you for joining World Alloys here on this presentation. If you guys do have any questions, please feel free to get them in the chat. We'll allow the next couple minutes for questions. If we don't happen to get into your question, please feel free to email us all at the help-tech@rolledalloys.com, and we'll get back to you regarding your questions. So if you guys have any questions, please feel free to throw them in the chat. We'll be sitting around and waiting for you for the next couple minutes.
So it looks like we have a question in the chat. And one of the questions that we have is going to be sulfidation and how the nickel content affects it. So long and short, the nickel reacts readily with the sulfur in the process. It does lower the melting point of the material, but the main thing to consider here is that the nickel forms a nickel sulfide that becomes molten at the surface. Once this becomes molten at the surface, it almost removes that protective oxide layer, therefore leaving it exposed to contamination. Does that help? We'll go to the next question. Oh, thank you, Les Priest. Thank you for your comment. I apologize. I thought that was a question. Thank you guys for joining us today. And please feel free to contact us if you have any questions after the presentation concludes. Once again, we'll leave our contact details up on the screen for the last couple minutes here so you guys can take it down if needed. Thank you all for joining us today.
Thank you.